Assalamualaikum. My name is Muhammad Syahrul Izam Bezakira and I will present about the introduction of our project, which is apple grading machine. So as we know, fruit size and shape are important quality parameter in agriculture sector. Back then, farmer used manual method or to be specific human effort to isolate any fruit based on its size and shape. So we have come out with an idea of apple grading machine which to overcome the problem of using a manual method. So this machine will help to improve the production sector since Apple has high demand in marketplace. So this machine need to be monitored by human rather than use human resources to grade manually. So this machine consists of some component which is a tank storage. Tank storage will store an apple that have been plucked by farmer. Then it will go through the inclined mills toward a shaking tray. This shaking tray will contain some holes, which is a small apple will go through the hole and the big apple will stay on the tray. So from this tray, the apple will separate into two sizes, which is the small one and the big one. Next, I will proceed with the objective and scope of our project. So the objective of our project is to sort and grade apple based on its shape and size, to study more specific about the control system of a machine, to create and combine the transfer function of a system and a PID. And the scope of our project is produce a complete transfer function of the control system and also a free body diagram of the machine and simulation work using MATLAB, the software of simulating on computer as a platform to create a system model.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hakim Fakri bin Shaimi. So I will tell about the literature review for this chapter. We have done so many researches on automated grading machines. So for the first research, we 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 refer to the Lemans and Distin from 2002, which they designed a real-time grading method based on features extracted from defects. So from the result, it shows that correct grading with a rate of 73% by using image. The grading apple by using a quadratic discriminant analysis. And next, we need to find the suitable type of grading. So we refer to the Xiongzhou, Yuqiao, Wang, and Mengzhou, which they design and test a three type of grading by weight, color, shape, and weight, color, and shape. So by shape, they're using a S4C2440 embedded controller which meet the demand grading with max relative error of single stage at 5.6%. And next, for the PID controller, we refer to the Ismail Kavdi and Daniel Egoya, which they apply a fuzzy logic as a decision-making support to grade apple quality. Grading outcome shows that 89% general outcome of the human expert, offering good versatility to represent the preference of expert and grading standard. And then we make a comparison between open loop and closed loop. So we refer uh, to the B. Borovic, A. Q. Lu, D. Popat, H. Chai, and F. L. Lewis from 2006 that they make a comparison and on open and closed loop for micro electromechanical system MEMS. So they mention that the ultimate step for improving precision and speed response is the introduction of feedback. And lastly, for the actuator, we refer to the Ham R, Sugar T, Vanderbilt, and B. Hollander K, and Lefebvre B from 2009, which the design of actuator with adaptable passive compliance. That's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Reza bin Arif. My metric number is DD180022. So now I will explain on the chapter 3, which is theoretical calculation. So for analyzing the behavior of the control system for this project, the mathematical modeling for this system need to be obtained by deriving the equation. So in order for us to know about the response of the control system itself, deriving equation will help in the later on to obtain the total transfer function. So to obtain the derived equation for this control system, the system is needed to be simplified into a free body diagram to acknowledge each component response. As mentioned before, deriving the equations will help us to um, to look and observe clearly on the detail of this control system. So the to simplify the derivation of the model, the following assumptions were done. First, the force is considered as force from the top of the armature motor, which is which brings the meaning of torque is equal to force times radius. Second, the mass of the shaker. Third, external friction is neglected. Fourth, external disturbance are neglected. So as shown on the right side is the block diagram of the control system without the PID controller. So this is the actual actuator, which is motor, and the right side, the equation on the right side is the early equation for the motor, and after undergoing some substituting of equation and Laplace transform, the the transfer function that we got is on the right side as shown on the screen. So the parameter contained in the total transfer function is first torque constant, electrical inductance, motor inertia, damping coefficient, electric constant, and lastly motor constant. Okay, next is the plant, which is the shaker. So after deriving the equation of motion of the plant, so um, i so the equation of motion got us into the equation of Ft on the left side, and after obtaining the equation, the Laplace transform is applied on the equation of motion, and after rearranging the uh, Laplace transform equation of motion, and the transfer function of the shaker is obtained. So the parameter contained in the in the transfer function of the shaker is first gravitational acceleration, mass of shaker, spring coefficient, force from top of motor, and lastly radius from the center of axle. So transient response is a response of a control system to any fluctuation from a steady state, and after applying input to the control system, output takes certain time to reach steady state. The output will be in transient state until it goes to a steady state. So after substituting the parameters into the total transfer function of the equation of the system, sorry, the equation will be looking as shown on the screen. So before adding the PID controller into the control system, the total transfer function is shown on the screen. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Hakim Mezweni and my matrix number is DD180014. So I will explain the determination of PID controller. PID controller is an alternative use in industrial control application to regulate temperature, flow, pressure and speed and other process variable. While all this to be seen is that the PID controller is able to eliminate the steady state error completely. It also has some disadvantages. One of it is it will make the system have a lot of poles compared to the one without the acceptance of PID controller. So diagram below show the full control system together with PID controller, and at the bottom the figure show the total transfer function including PID. Next, the proportional gain controller control the steady state error and eliminate the percentage overshoot of the system. The diagram below show the control system with proportional controller KP. So in this case, the value of KP is chosen based on assumption, and for the first trial the value chosen is 1, as the value KP is equal to 2, the error obtained is 0.38, which is similar when the controller is absent. So you can see graph 3.3 show MATLAB simulation with proportional gain. So next, compared to the proportional derivative controller, the proportional derivative controller is lacking at making minute adjustment to the steady state of the system, thus making it impossible to eliminate the steady state error. So the diagram below show the control system with controller KP and KD. After the MATLAB simulation is done, the value of KD is set to be 1. When the KD is set to be 1, the steady state error is successfully eliminated from the system, and it can be seen from the graph generated by the Simulink. The graph is as shown as below graph 3.4, MATLAB simulation with proportional and derivative gain. Therefore, the arrival of integral controller Ki that combined with the other two controller eliminate the steady state error. This shows that by applying the PID controller will cause the transfer function of the system to be affected. Below are the value used in all controller. After applying integral derivative controller to the system, supposedly this allows the controller to eliminate the steady state error completely, but instead the graph gain overshoot. However, the graph reached its steady state at the amplitude of 1. So after undergoing some trial and error method, the best value to be set for the Ki is 0.5. The steady state error can be discarded completely when K is set to 0.5. So graph 3.5 show the MATLAB simulation with PID gain.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Saifuddin bin Sukito, and I'm going to present the computational analysis by using MATLAB. By using the same transfer function that we get from the previous chapter, we put inside the value in the Simulink of the MATLAB software. For the open loop control design, it takes about 7 seconds to rise and reach the peak at 35 seconds, which is 0.63, and settling time takes about 38 seconds, and the final value of steady state is 0.62. Next is closed loop. For the closed loop controller design, it takes the same time as the open loop, which is 7 seconds to rise, and difference in value of peak and settling times, which is the settling time for the control loop designs taking shorter than the open loop, which is 35 seconds, and it reached the peak at 28 seconds, which is 0.38, and the steady state of the final value is 0.37. And for the closed loop with the PID controller design, it takes shorter time to reach the peak, which is 15.7 seconds at 1.071, and the settling time is about 30 seconds. That's much shorter than the open and closed loops that without the PID controller. And the steady state is at 1. Okay, for the comparison between the open loop, closed loop with the PID controller is the outcome of the graph might be slightly different in value because of the open loop does not have feedback, and the closed loop has feedback, and the closed loop with PID controller has the system that manipulating the damping ratio of the system. In the method of the overshoot error, for the closed loop and open loop, we get the graph without the overshoot error. Meanwhile, with the PID controller of the closed loop, we have sums of the overshoot error. This is because the PID controller is responsible for controlling the steady state error of the system by manipulating the damping ratio of the system. Okay, next is the PID controller would also trigger the system poles to move to the S negative plane side, making the settling time shorter, and it's sensitive to the system to reach the steady state. It makes the system to reach the steady state become more faster. and it eliminates for the other system it can eliminate some the overshoot error, but for our system the PID controller come up with the a little bit of the overshoot error. Okay, that's all for me. Thank you.
Lastly is conclusion and recommendation. So for the conclusion, I can conclude that all objectives of our project have been achieved, and the control system of the machine also working well, and we able to use MATLAB to generate graph for our system, and we also able to combine the transfer function and the PID control in our system. So for the recommendation, we need to improve some part because some errors occur when we run our system. So the first is we need to come out with accurate parameters since some error occur while running the system to make it run smoothly. And then we need to improve the design of the grading machine because it need to operate 1,000 number of apple daily. That's all from us. Thank you.